Hi guys, today is April 1st and we're doing testing convergence at endpoints, day one, okay? And really we're not gonna get to the endpoint thing today, that's really gonna happen tomorrow. It's just, this is one section in the book, okay? And so we're gonna go back over and look at some of these tests for convergence that we've been using over the last month or so, okay? All right, so the integral test is the first one we want to look at, okay? And if f is positive, continuous, and decreasing for x greater than or equal to, and I'm going to change this a little bit, okay? So I want to change this because it doesn't have to be 1. This makes you think it has to be 1, and it doesn't, okay? It has to be x is greater than or equal to some n, where n is a positive integer. So I've changed this already for future years, but I want this to be n, okay? So it could be x is greater than or equal to 2, x is greater than or equal to 3, x is greater than or equal to 4. If that's true, okay, then that's going to change some things. So we're going to do from here, n equals 1 to infinity. It wouldn't be 1 anymore. It'd be n equals this integer value, okay? And we had some problems where we had to start it at 2 and jump all the way to 2 and not start it at 1. That's okay, as long as for some integer on, this is true, okay? And so n equals n, that integer, like this is going to be true for x greater than or equal to 3. Then this would be n equals 3, okay? Or something like that, okay? All right, right here, this wouldn't be 1 now, okay? That would be capital N instead. I should just cross it out instead of putting an X, okay? All right, so capital N there, okay? So if this is going to be from 3 to infinity, we're going to integrate from 3 to infinity. And integral test says if f is positive, continuous, and decreasing, then the series and the integral, okay, either both converge or both diverge. So we can do the integral to determine if it converges or not, okay? All right, so here we go with the first one, okay? And does, example 1, does n equals 1 to infinity of 1 over n squared converge, okay? So what do we know? We have a sub n is equal to 1 over n squared, okay? So our f of x is going to be 1 over x squared, okay? So what do we know about 1 over x squared? Is it positive? Yeah. For x greater than or equal to, and we're going to pick 1 here. It's true for 1 on, okay? 1 over x squared is greater than 0, okay? And what is that saying? It's saying it's always going to be positive, okay? Is it continuous? Yeah, there's only a break at 0, and we're not including 0, right? Okay, so it's going to be 1 over x squared is continuous. And what else do we know about 1 over x squared? It's also decreasing because the denominator just keeps getting bigger and bigger and bigger and bigger and bigger, right? So, and 1 over x squared is decreasing. Okay, and for what x values is this happening? Well, it's for all x's greater than or equal to 1, okay? So this meets the conditions for us to use the integral test, okay? All right, so we're gonna do since x is greater than or equal to 1, we're going to integrate from 1 to infinity of 1 over x squared dx. Okay, we're going to change this becomes a limit. So this is a review on improper integrals. This becomes the limit as b approaches infinity of the integral of 1 to b of x to the negative 2. And then, okay, so what does this mean? This means we're going to add 1 and divide to do the integral. We're going to add 1 and divide by that new power. So this is going to be x to the negative 1 over negative 1. And you know what? I forgot. Let me take this off. Let me change this. We need to fix this because I forgot the limit statement, right? I forgot the limit. Okay, so this becomes the limit as b goes to infinity of, and this becomes x to the negative 1 over negative 1, evaluated from 1 to b. Now, this is 1 over x divided by negative 1. That'd be just negative 1 over x. So this is equal to the limit as b goes to infinity of negative 1 over x evaluated from 1 to b. Okay, so this is equivalent to the limit as b goes to infinity of negative 1 over b, and then minus negative 1 over 1. That's equivalent to the limit as b goes to infinity of negative 1 over b, and this would be just plus 1. Now, as b goes to infinity, okay, as b goes to infinity, this is going to get, this denominator is going to get bigger and bigger and bigger, which is going to cause this fraction to get closer and closer to 0. So basically it's 0 plus 1, or this is equal to 1. Okay, now what does that tell us? That tells us that 1 to infinity, 1 over x squared dx, that integral converges because we've got a number value out of it. Okay, and then by the integral test, we now know that the series must also converge. Okay, so we'd say sigma, let me slide this up so you can see it, sigma n equals 1 to infinity, 1 over n squared, converges by the integral test. Okay, and that's the first example. Okay, so I want to say this. If you're really comfortable using this integral test and you're good, you can fast forward and go ahead and go to the P-series test, which is on the 4th page, I believe, okay? Yeah, all right, and just fast forward to that. If you're like, I got this, Mr. Mitchell, then go ahead and go for it. I know this is kind of a review. I just want to keep it fresh in our minds, okay? All right, so example number 2, all right? So does the series n equals 1 to infinity of 1 over n to the 1/2 converge, okay? So this is a candidate for the integral test, okay? So we're going to let f of x equal 1 over x to the 1/2 power, okay? And what do we know about f of x and 1 over x squared? We know f of x is greater than 0, which would mean it's f of x is positive. This is, I'm writing it a little bit differently, okay? We also know that this function is continuous except for x equals 0, but we're not going to include x equals 0, right? Because we're starting this at 1, okay? So f of x greater than 0, f of x is continuous. And then is it decreasing? Okay, so one way to look at it is you can pull this up and look at your graphing calculator of 1 over x to the 1/2, and you would see that from x greater than or equal to 1 on, it's decreasing, okay? You could also take the derivative of this and show that from 1 on, that the function is always, I'm sorry, not the function, but the derivative is always negative. That would also tell you it's decreasing. So just another way of showing that it's decreasing, okay? So f of x is continuous, and we would say f of x is decreasing. For or on x is greater than or equal to 1. And if you think about it, when x is greater than or equal to 1, this denominator gets bigger and bigger and bigger, which the overall fraction gets smaller and smaller and smaller. So it would have to decrease, okay? Right? Just kind of rationalizing it out, okay? Just using logic. All right, so now we need to do the integral, okay? So we're going to do the integral from 1 to infinity of 1 over x to the 1/2 dx. That becomes a limit as b approaches infinity of 1 to b of, I'm going to rewrite this as x to the negative 1/2 dx. Okay, so this is equal to the limit as b approaches infinity of, and we're going to add 1 to this. So that's going to be, I'm going to start a bracket here, x to the 1/2 divided by 1/2. But dividing by 1/2, it's better to multiply by 2. So 2. Okay. And we're going to evaluate that from 1 to b. So this integral is equivalent to the limit as b goes to infinity of 2b to the 1/2, and that would be square root, okay, minus 2 times 1 to the 1/2 power. Well, 1 to the 1/2 power would be 1 times 2, so this would be just minus 2, right? So this would be the limit as b approaches infinity of 2b to the 1/2 minus 2. Well, what happens as b goes to infinity? Well, you're square rooting it, right? So this number is going to get bigger and bigger and bigger, which is going to make b to the 1/2 become bigger and bigger and bigger, which is going to make times 2 is going to be bigger and bigger and bigger, minus 2. So this minus 2 is insignificant. So this turns out to be equal to or equivalent to infinity, all right? Well, what does that tell us? That tells us that the integral diverges. It doesn't converge, because if it converges, that means the integral will give us a number, all right? So this is the integral from 1 to infinity of 1 over x to the 1/2 dx. And we now know, because of what we got here, that it diverges. And what does that tell us about the original series? Okay, so since this one's series, I'm going to scoot it up a little bit. Okay, since this integral diverges, that tells us that the series n equals 1 to infinity of 1 over n to the 1/2 diverges by the integral test. And so if we looked at this example 1, we had a power of, I think it was 2. Yeah, power of 2. This one we have a power of 1/2 for our denominator, right? And I'm going to show we're leading up to the p series test, okay, to show it, all right? Okay, so we're going to go to example 3 now. Okay, so for example 3, does n equal 1 to infinity sigma of 1 over n converge, right? Okay, so again, this is integral test, okay? So the integral test, we got to show f of x is going to be 1 over x. And what do we know about this? Is it positive for x greater than or equal to 1? Or for some x bigger than 1? Yes, okay? Or I shouldn't say bigger than 1, because any positive integer that's bigger than 1. So like 2, 3, 4, okay? And that's true. That's true for 1 on, right? For if you put 1 in here, if you put 2 in here, if you put 3 in here, okay? F of x is going to be is positive, right? Or greater than 0. You could say it's positive, or you could say it's greater than 0, okay? We also know it's continuous. So f of x is continuous. You have to state all of this in order to meet the conditions to use the integral test. This is really important. You got to say all this stuff, okay? Because without this, you can't necessarily say that you can use the integral test. This is what's leading us to say, hey, we can use the integral test on this series, okay? So f of x is continuous. And then we also know that f of x is decreasing, because x is going from 1 to 2 to 3 to 4 to 5, right? And so this denominator is getting bigger and bigger and bigger, which makes the fraction get smaller and smaller and smaller and smaller and smaller. So the only way for that to happen is our function would have to be decreasing, right? So f of x is decreasing. Okay, and it's all of these. It's positive, it's continuous, and it's decreasing for x is greater than or equal to some integer value. And in this case, it's just 1. Okay, a lot of times it is 1. Okay, but it doesn't have to be. Like if we need it to start at 3 and go 3 on, it works. Okay, we can do that. All right. Okay, so this leads me to say, hey, I can use the integral test on this. Okay, so it's my integral is going to start at 1. to infinity, and it's 1 over x dx. Okay, that becomes the limit as b goes to infinity of the integral of 1 to b 1 over x dx. That's going to become x to the negative 1. So limit as b approaches infinity, the integral from 1 to b of x to the negative 1 dx. Okay, so we're going to add 1 to this power, right? And divide by it, right? So add 1, you get 0. Divide by it, you get 0. And is that right? And it's not, right? So really, I jumped in and started doing this, but we need to recognize, hey, wait, this is the antiderivative of what? It's the natural log, right? So doing this, changing it to a power and trying to use the power rule won't work, right? So let me cross this out, because that happens a lot more than you think. This happens, okay? Just catch yourself. Like if I add 1, that's going to give me 0, and I'm going to divide by 0. Wait, I can't divide by 0. Okay, so you should think that. So there's got to be another way, right? And it is. The integral of this is the natural log of the absolute value of x. Okay, so this becomes, instead of trying to use the power rule, which doesn't work, okay, we're going to take the limit as b approaches infinity of the natural log of the absolute value of x from 1 to b. Okay, so this becomes the limit as b approaches infinity of the natural log of the absolute value of b minus the natural log of the absolute value of 1. Okay, now this is, I'm going to slide it up a little bit. This is the limit as b goes to infinity of the natural log of, now b is going to infinity, right? So really we don't need the absolute value around this b, okay? So I'm just gonna write b. And then minus the natural log of 1. But remember, the natural log of 1 is equal to the natural log of e to the 0, because e to the 0 is 1, so that's 0, right? So this is minus 0. Okay, so the limit as b goes to infinity of natural log of b. Well, what happens as b goes to infinity for natural log? It just keeps getting bigger and bigger and bigger and bigger and bigger. Slowly, but it gets bigger, okay? So this is infinity, which tells you that the integral diverges, okay? So the integral from 1, let me slide it up a little bit, 1 to infinity of 1 over x dx diverges. And because of that, we now know that sigma n equals 1 to infinity, 1 over n diverges by the integral test. Okay, so these first 3 examples, okay, they were all 1 over n to a power, right? Okay, so those are powers, okay? And if we looked at the first one, if the power was 2, it converged. If the power was, and that 2 was actually bigger than 1, right? So if it's bigger than 1, it converges. What if it's between 0 and 1? Like this one is 1, right? What happened? It diverged, right? So again, if our powers are between 0 and 1, including 1, it's going to diverge. And so we don't have to do the integral test anymore. We're going to change this. And I was showing you these 3 examples because that leads us to the p-series test, okay? And so turn the page and we're going to talk about the p-series test. All right, so the p-series tests, okay, and I say here, p-series are just an extension of the integral test, right? So they came from the integral test, but we can come up with specific rules where we don't have to do the integrals anymore, okay? So these integral tests, it's an extension of the integral test. It's used frequently with the direct comparison test and the limit comparison test, okay? We're gonna discuss that later today, okay? So if a sub n is in the form 1 over n to the p, right? And that p is less than or equal to 1, then we know automatically from, and it comes from the integral test, that this series every single time will diverge. If this p is bigger than 1, then we know um, it will converge every single time. If you have into the p power, into the third, into the fourth, into the fifth, into the second, okay, those will all converge, okay? All right, so let's go to example 4, and let's do that. And you know what? Let me underline this. I had this in my other notes, okay? We're going to use this along with the direct comparison test and the limit comparison test. Okay, that's so when you go and you go, could I use the limit comparison test or the direct comparison test? You should be comparing it probably with something that you know really quickly converges or diverges, and that's the p-series test. Okay, that we can tell really quickly if it's going to converge or diverge. All right, so let's go to example 4. So this is a very, very useful test, okay, this p-series test. All right, so we have here n equals 1 to infinity of 3 over n square roots of n, right? So we're going to rewrite this, okay? Now, what we need to do is, because square root is really a fractional exponent, right? So we're going to be able to combine these and make it into a power, okay? And that's the whole idea of it, all right? So what we have here is sigma n equals 1 to infinity of 3 over n square root of n. That's equivalent to sigma n equals 1 to infinity of 3 over, and this is 1/2, and this is 1, right? So we would add the exponents. So 1 plus 1/2 gives you 3/2. So this would be n to the 3/2, okay? Now, what can we do with this 3? Okay, this 3 can come out in front because every term is going to have a 3 in it, right? Okay, so what that means is you could, since every term, if you start with n equals 1, 2, 3, right? Every one of them is going to have a numerator of 3, which means you could factor that out and make a new series, right? So this becomes 3 times sigma n equals 1 to infinity of 1 over n to the 3/2 power. Okay, so we have 1 over n to the p, right? What's our p value? Okay, p is 3/2, and it's bigger than 1. So that tells us it converges, okay? So since p, in this case, equals 3/2, and the fact that p is greater than 1, you need to state that, right? Okay, then we know that this series, sigma n equals 1 to infinity of 3 over n square root of n, converges. We know it automatically converges without having to do the integral test, and it's by the p-series test. Okay, all right, and that's the first one. Let's go to example number 5. Okay, before we go to the next example, we're going to talk about, again, the limit comparison test, okay? And this is one of the most useful comparison tests. This is actually, I think, easier to use than the direct comparison test, okay? But suppose, and okay, when you do this, you got to show the series that you're comparing and the convergence or divergence of that series, okay? So A sub n, when we talk about A sub n, that's the one we're trying to figure out, okay? B sub n is the one we're going to compare it to. That's the one that's going to be the known one, okay? All right. And so these are positives. So the terms are all positive for some n, lowercase n, greater than or equal to n, where n is a positive integer. Okay. So a lot of times this capital N is going to be 1. Okay. But it could be 2, could be 3, could be 4. Okay. All right. So if we look at the limit as n goes to infinity of the series we're given over the series that the nth term, let me rephrase this. If we take the limit as n goes to infinity of the nth term of the series that we're given and compare it to the nth term, which we're going to divide by it, the nth term of the series we're comparing it to, and that comes out to be a number between 0 and infinity, so it basically comes out to be a positive number, okay, then they behave the same way. So this is the one that we're going to know about, b sub n. So if it converges and we get a number here, then a sub n also must converge. If b sub n diverges, then a sub n must also diverge. So they're doing the same thing, okay? They're either both converging or they're both diverging, okay? If the nth, if we take the limit as n goes to infinity of the nth term of the series we're given, divided by the nth term of the series we're comparing it to, and it comes out to be 0, okay, then and the fact that b sub n converges, a sub n converges. So if we get 0, if this one converges, then this one converges. Now we can't use this if this one's diverging. So the one we're comparing it to must converge, okay? All right, so if the limit as n goes to infinity of the nth term of the series that we're looking at divided by the nth term of the series we're comparing it to, and it goes to infinity, and b sub n diverges, right? The one we're comparing it to is diverging, then the series we're looking at must also diverge, okay? So here we go. All right, example 5. All right, so determine if sigma n equals 1 to infinity of 3n plus 2 over n plus 1 squared converges. So our a sub n is equivalent to 3n plus 2 over n plus 1 squared, okay? And what do we know? A sub n is greater than 0. It's positive for all n greater than or equal to 1, okay? All right, now what's our b sub n? What do we want to compare it to? Well, it's really helpful to use a power series, okay? Or not a power series, the p series test, okay? And so we want to rewrite this as some number over into a power, okay? So if you look at this, we could rewrite b sub n as 3n over n squared, okay? So 3n over n squared, which actually becomes 3 over n. Now this power is 1 right here for n, right? And from the last problem, we know that this one is going to diverge, right? And so b sub n, I should say this, b sub n is greater than 0. So both these are true for n greater than or equal to 1. And we should say this, for n greater than or equal to 1. Okay, and what do we know about b sub n? Okay, so we know that the series n equals 1 to infinity of 3 over n is equivalent to 3 sigma n equals 1 to infinity of 1 over n, and our power of n is, or our power for the n is 1 right here. So we know p equals 1, and 0 is less than, p is less than or equal to 1, okay? So we know this series n equals 1, 3 over n equals 1 to infinity, 3 over n diverges by the p series test. Okay, so now we gotta look at the ratio of a sub n over b sub n as n goes to infinity and see what we get for that, okay? All right, so I'm gonna slide this over a little bit. Okay, we're gonna take the limit as n goes to infinity. Here's my main fraction bar, okay? A sub n is 3n plus 2 over n plus 1 squared. And my b sub n is 3 over n. Okay, so this, because we're doing a ratio of two fractions, we could write this as a multiplication problem. It's kind of like the ratio test, okay? So this is gonna be the limit as n goes to infinity of 3n plus 2 over n plus 1 squared times n over 3. Okay, so this would be the limit. I'm going to rewrite this. I'm going to rearrange the numerators and denominators. So the limit as n goes to infinity of n over n plus 1 squared times 3n plus 2 over 3. All right. And this and then this becomes equal to the limit as n goes to infinity. Okay, so I'm looking at this. Okay, if I multiply n times 3n plus 2, right? If I multiply these two, I'm going to get an n squared. Okay, that's going to be helpful. All right, so I'm going to actually multiply this numerator n and this numerator 3n plus 2 together and get 3n squared plus 2n over n plus 1 squared. Times, okay, so this isn't the same equivalent to this yet, right? Because these two I multiplied together, that's my numerator, this is my numerator. So what happens here is this becomes 1/3, so times 1/3. Now what happens as n goes to infinity? Well, this is 3n squared over n squared, right? And we look at the magnitude of the numerator and magnitude of the denominator. They're both n squared. So this becomes 3. So this becomes 3, because as limit as n goes to infinity, the 2n and all the extra terms here in the denominator are going to cancel out. You're going to be left with 3n squared over n squared, which becomes 3 times 1/3, which is equal to 1. Now, what does that tell us? Okay, so for the limit comparison test, this came out to be a number, right? It came out to be a number between 0 and infinity, all right? So it came out to be a positive number. And what that tells us is they behave the same way. So what do we know about the series we were comparing it to? It diverges. So this one must also diverge. And we can make that conclusion now. Okay, so sigma n equals 1 to infinity of 3n plus 2 over n plus 1 squared diverges by the limit comparison test. Okay, and that's example number 5. Boy, I am writing crooked today. Sorry, guys. All right, let's take a look at example 6. All right, for example 6, determine if sigma n equals 1 to infinity of 1 over 2 to the n minus 1 converges, okay? So what we know is that we're going to let a sub n equal 1 over 2 to the n minus 1, okay? And for n bigger than or equal to 1, this a sub n is greater than, so a sub n is greater than 0, right? It's positive. For n greater than or equal to 1. So starting at 1 on, yeah, it's always going to be positive because this number is always going to be bigger than this one, okay? All right, so we want to compare this to something, okay? So b sub n, right? All right, so something to look at is we have 2 to the n power here, right? What I want to compare it to, b sub n, would be 1 over 2 to the n. All right. Now, why? Because this is also 1 over 2 to the n can also be written as 1 to the n over 2 to the n. And that can be rewritten as 1 over 2 raised to the n power. And that tells us it's a geometric series, right? Okay. So we know this is going to come out to be a geometric series. We also know that b sub n is greater than 0 for n greater than or equal to 1. Okay, so for both these, n greater than or equal to 1, the terms are all going to be positive, okay? All right, and what do we know about this one? So this one is sigma n equals 1 to infinity 1 over 2 to the n is equivalent to sigma n equals 1 to infinity of 1 over 2 to the n. And what we know about this, it's a geometric series. All right, so this is a geometric series. N equals 1 to infinity. 1 over 2 to the n is a geometric series with r equal to 1/2. And since the absolute value of r is less than 1, because the absolute value of 1/2 would be 1/2, the series sigma n equals 1 to infinity, 1 over 2 to the n converges by the geometric series test. Okay? Now, so now we're going to compare them, right? So we're going to take the limit as n goes to infinity of a sub n, which is 1. Let's write a fraction bar here. Let me slide it up too. I'm still writing crooked. Sorry, guys. Tried to correct that. So 1 over 2 to the n minus 1, right? That's my a sub n. That's my nth term, okay? And then my b sub n, my nth term, would be 1 over 2 to the n. Okay, so that's equivalent to the limit as n approaches infinity, 1 over 2 to the n minus 1 times 2 to the n over 1, right? Because I got to flip my fraction. Okay, so that's equivalent to the limit as n approaches infinity of 2 raised to the n power over 2 to the n power minus 1. Okay, all right, so this is controlling the growth in the numerator, and this is controlling the growth in the denominator because n is going to infinity, right? So we look at magnitude, okay? This minus 1 is really insignificant. So really, as n goes to infinity, right, the numerator and denominator pretty much match perfectly, okay? I mean, they don't if you stop it, but if you go to infinity, this is going to get closer and closer and closer. And if you do go to infinity, this would equal 1, okay? So what does that tell us? Okay, so if we do this limit comparison test and it comes out to be a number value like this, positive number, okay, that tells us they behave the same way. Well, what did we know about the series that we were comparing it to? It was converging, right? So our series must also converge, okay? All right, so sigma n equals 1 to infinity of 1 over 2 to the n minus 1, it must converge, right? It converges by the limit comparison test. So it's really, really important. The series that we compare it to, all right, we have to show that that series either converges or diverges. So we gotta determine the convergence of this b sub n, right? We gotta determine the convergence of this, and that's what all this is. And then we're doing the limit comparison here to determine the convergence of our actual series. All right. Okay. So let's go on to example 7, and then we'll be done for today. All right, so for example 7, determine if n equals 1, sigma n equals 1 to infinity 2n plus 1 over n cubed minus 2n converges, okay? All right. So we know that a sub n is equal to 2n plus 1 over n cubed minus 2n, okay? And a sub n is greater than 0. Okay, now here's an example of it doesn't work for n greater than or equal to 1. Why? Okay, so if we put 1 in here for n, right? 1 cubed is 1, minus 2 times 1, that's 2. So this would be 1 minus 2, right? And that would give us negative 1. Well, a sub n would not be positive, right? But how about for n bigger than 2? Well, what's 2 cubed? 2 cubed is 8 minus 2 times 2. So for every n after that, okay, it is going to be positive, okay? So I'm going to pull up the graphing calculator, and I'm also going to show you, like, okay, where is a sub n positive, right? Okay, and it will be after n equals 2, it will be positive for all the rest of them, okay? Okay, from our home screen on this, okay, what we want to do is we want to press mode, okay, and then we want to go down to, and we want to select sequence, and then press enter, okay, and this is going to graph our a sub n terms, okay, and then for u sub n, let's go ahead and type in 2n plus 1 over n cubed minus 2n, all right, and then we want to go to our window, and then we want the n min to be 1 and the n max to be 10, because and you could go further than this, okay, you can go further than 10, but x min, let's set that at 0, and x max, let's put that at 10, and then y scale at 1, y min, let's put that at negative 3, and we're just going to start here with the y min being negative 3 and our y max being 3, and then y scale be 1s, okay? And let's take a look at the graph of this, okay? So if you look at this, okay, right here, this is our first term, and notice it's negative, right? But then our second term is this, and it's positive, right? And if you look at this, it's going to be positive all the way across, right? But a sub n is getting smaller, but if we go along and trace here, right, we could trace it and see the values, okay? So notice the first y value is negative, and the second one is positive, and positive, and positive, and positive, and positive, because that n cubed is going to be more powerful than minus 2n in the denominator. All right. So after a certain value, like that takes on, that's more that. Sorry, I'm stuttering. Okay, so the n cubed is causing a faster growth than the minus 2n is in the it's about the magnitude of it. Okay. All right, that one's going to grow faster. So you just look at this, and it's just going to keep going. It's going to keep being positive. All right. Okay, so that's just showing you that a sub n is greater than 0, but not for n greater than or equal to 1, but for n greater than or equal to 2. Okay, and that's why I wanted to do this example. So back to this series. Okay, this is true for n greater than or equal to 2. So our terms are positive, but it's not for all of them. It's just for n greater than or equal to 2. Okay, so what do we compare this to? Okay, so we really want to maybe take a look and see, all right, we have n to powers, right? So we really want to look at the magnitude of this, right? And for the numerator, it's 2n, and for the denominator, it's n cubed. So let's let our b sub n be 2n over n cubed. Now, what does that become? That becomes 2 over n squared, right? Okay, and all right, so this is, so we know as n becomes 1, 2, 3, all of these are going to be positive, right? So b sub n is also greater than 0, and it has to be for the same n value. So this is greater than 0 for n greater than or equal to 2. Because if this is actually true for n greater than or equal to 1, but if it's greater than, if it's true for n greater than or equal to 1, it must also be true for n greater than or equal to 2. Okay, so this is the series we're going to compare it to. Now, what do we know about 1 over n squared? Okay, 1 over n squared is going to converge because our p is bigger than 1, right? P is greater than 1. Okay, and that tells us that series is going to converge. So this is the actual series. This is the series we're going to compare it to. So we got to determine the convergence of this one by writing that. We can't just say it like we just did. Okay. So what we have here is sigma n equals Okay, and this is actually going to be for 2 to infinity. Okay, and we have 2 over n squared. Okay, that could be rewritten as 2 sigma n equals 2 to infinity of 1 over n squared. And we know that p equals 2 and p is greater than 1. So we know that this series n equals 2 to infinity 2 over n squared converges by the p series test. Okay, so we've established the convergence of the nth term of the series we're comparing it to, right? We've decided that we've stated and shown that this one converges, okay? So now we got to look at the ratio of them, right? The a sub n over b sub n as n goes to infinity, okay? And then we're going to take a look at that and see what this tells us, okay? So we're going to do the limit as n goes to infinity of, okay, our a sub n, which is 2n plus 1 over n cubed minus 2n, all over and 2 over n squared. Okay, so that means this is the same as the limit. I'm going to slide this up a little bit. As n goes to infinity of 2n plus 1 over n cubed minus 2n times n squared over 2. Right? Okay. So what's going to happen is I'm going to bring this in over here. Okay. I'm going to distribute this because what if you're looking ahead, if I distribute it, right, n's going to infinity. So we're going to look at the biggest power of this compared to the biggest power of this, right? And if we multiply n squared, this is going to become 2n cubed over n cubed. When we do the limit as n goes to infinity, this sucker is going to go to 2, right? Okay, so kind of looking ahead, right? I'm going to want to distribute this, but I want to keep the 2 here, all right? So actually, I take that back. We could actually multiply it out, okay? So this could be the limit as n goes to infinity, 2n cubed plus n squared, right? 2n cubed plus n squared over, if we multiply the 2, that's why I said this, if we multiply the 2, we get 2n cubed minus 4n, right? But what's really important is this 2n cubed and the 2n cubed here, right? As n goes to infinity, well, what's going to happen? These are going to cancel out and you're going to be left with that's equal to 1, right? Okay, so we did this limit comparison, right? All right, and we got a value of 1. What does that tell us? That tells us that a sub n and b sub n behave the same way. So they either both converge or they both diverge. Well, what do we know about b sub n? It converges by the p-series test. Therefore, we now know that the series we were comparing it to must also converge, okay? So we'd say sigma, and actually this one, I know this one was n equals 2, okay? But actually this one will converge for n equals 1 also, right? Okay, okay. So we're gonna do n equals 1 to infinity of 2n plus 1 over n cubed minus 2n, okay? And we know that it converges by the limit comparison test. Okay, and that's example number 7. And that's it for today. Let me get the assignment sheet. We'll pull it out and we'll talk about that. Okay, so what I want you to do is assignment 11-7, and today is the 1st, so 4-1. And I want you to do page 528, but I'm going to change this a little bit, okay? I want it 1 through 17 odd. Okay, only 1 through 17 odd, okay? All right, guys. So you guys take care, and I'll see you, or I guess I won't see you, huh? But I'll talk to you next meeting. Okay? Take care, guys. Bye.